Okay, we started. Let me see one thing here. I'm gonna turn off my video. Let's see if I can get the video there in this one here. See if we can. Oh yeah, good. Yeah. Yeah, let me show you something, folks. This is the window of my video screen capture software, and you do have my picture in there, but that's because I turned off my webcam in Zoom. Okay, when I turn on the webcam on Zoom, this guy doesn't show up. Okay, at the beginning I didn't have this problem, and then now I suddenly start having. I do not know why. So here you go. That today is the 28th. And we're going to do the handout number 6, parallel in circuits and series. This is something that we do in real life, and I have some things here to show to you, okay? How we get circuits in series and parallel. I want to show you in real life how this thing happens. Let me get my stuff here. So when it comes the moment I will switch back to the camera of my Zoom software, of my Zoom lecture. Now let's go get the handout number 6. Right, go ahead, go there on your side to the last time was on the 26th. Okay, 26 right in here. Remember, 4 important devices in electronic and electricity: capacitor, resistor, elements, right? Inductor and resistor. You already are familiar with the capacitor and the resistor. With those 4 devices, you can do whatever you want. You can build a cell phone, you can build a TV, you can build all those nice electronic gadgets that we have out there. And lab 2 I still didn't correct it. I'll get it soon. Let's see what's due today, right? Lab 2 was due on the 22nd, so I'm gonna get it corrected soon. Lab 3 was due yesterday, the 27th. Report of lab 4 is gonna be due tomorrow. So this weekend I will correct those 2 here and post that for you. Lab report number 6 is going to be due on the 5th of August. Okay. And let me just tell you which one we're going to skip. Let me see, maybe it's already in our syllabus, right? Let's see here. Let me pause. Okay, reflection. Okay, I'm making this one on the 12th. Well, I'll let you know later on. For now, let's assume that parallel series circuits is the one, and let's get the handout. 6. right in here. Resistors in series and parallel. Okay. Let me brief you quickly how you already know more or less what happens when we put a circuit together. Okay, so I'm going to make a demonstration of how to do that. Okay, so here you go. Let's see. The objectives of this virtual lab are what? Practice how to build electric circuits to resistors connected in series or parallel. So what we did before, we connected just a single circuit, a single resistor to your circuit. That's what we did before. But now we are going to combine different resistors to the circuit. Okay, that's what we are going to do. And both in series and parallels. Okay, to get more experience measuring current, yeah, we're going to measure current and voltage. Learn how to find power supplied by battery and power loss in a resistor. Yeah, we're going to cover that in more detail also in our lecture. To this end, we open the circuit construction kit we used last time by clicking here. Let's go there. I'll walk you through how to do that. Here you go. That's my desktop, right? The table that we put together our circuit, my virtual table that we put together our circuit. So let's go back to our click play, and to this end we open the circuit. By click and you see what you saw in the previous virtual lab. Click play and it will take you to the same window. Okay, we're already in the window. Resistors in series. Resistors in series. You already know how a resistor look like. I showed that to you before. Okay, resistors in series is when you put one resistor after another. That's what it is. Two resistors and a switch. Build the circuit showing figure 11.3. 11.3 is this one right in here. Okay, here you go. And remember to select any of these elements, click on there, and drag to the place you want it to be. Here you go. So let's go ahead and do it. The wire. Oh, but don't forget the battery, the source of what we call a voltage, source of electric power. Here you go. Nope, not this one. This one here. Okay. Connect another wire here. And we're going to get a switch. I like this simulation here of circuits. It's very simple. The only problem with the simulation is that it's too limiting. It could be a little bit more complicated, you know, have a little bit more of details, but I think it's a good way of learning circuits. Here you go, wires. Those are all wires. I have wires here in my lab. We're gonna get a resistor. Here you go, put a resistor. Resistors in series is when you put one resistor after another, like that. Okay? It doesn't matter. Oh, it doesn't matter if it is, you know, the way I did or the way that is illustrated here in the book, in the handout. Doesn't matter. Either way is still a circuit in series. So let's do according to the handout. Here you go. Here you go. Okay. Have a wire connected here. And we have our circuit. Right now the circuit is open. And again, what you have to visualize, when you close the circuit, oh, don't forget, I'm going to put conventional direction, right? When we close the circuit, and my battery is still 0 volts. When you close the circuit, you're going to power a current through this circuit. You're going to get electric charges moving in the circuit. And those electric charges are going to do some sort of work, are going to do something useful. Okay? This circuit here doesn't do anything useful. The only thing useful that this circuit does is just for educational purposes, for you to understand how an electric circuit works, how an electric and electronic circuit works. But if you want to do something useful like producing light, if you want to build a radio and things like that, then the circuit is going to be far more complicated than that. What you have right in here is something that has use only for educational purposes, for didactical purposes, for you to understand how the basic of all circuits work. Okay? The simples of all circuits, here you go. I'm going to show you the simples of, it was what we did before. The simples of all circuits is this one here with a single resistor. That's the simplest circuit you're going to see in your life. Okay? And now we are going to work with something a little bit more advanced. The next step in difficulty. A circuit with two resistors in series. So let's document what we said here in the notes. Okay, today is the 7/28. Don't underestimate those notes, okay? We learn much better. It doesn't matter if it's a student or instructor, just a child, or if it's a professional. We learn much better when we read something than when we listen. Okay? Not only read, but you also have to take notes along the way and try to explain in your own way. So here you go. We are doing lab number. Upload your lab report. Let's see. Today is the 28th. Let me see here. 29. Yeah, lab report for lab 4 due tomorrow. Here you go. Report for lab 4 or 5. Let's see. Go back here. Lab 4. Lab 4 due tomorrow. Okay, lab was not corrected yet. Not corrected yet. Those are my notes of last semester. Okay. I'll try to get it this weekend. And I'll try to get it corrected this weekend. And I will try. Here you go. Lab reports for labs 2 and 3 were not corrected yet. I'll try to get them corrected before the end of this weekend. Report for lab 4 due tomorrow. That's how you should upload it. Download handout for lab 6. That's what you're doing. Okay, yeah, don't worry about that. What's the material you're seeing right now in the lecture? Okay, here you go. Run the simulation, right? Background, background. previous lab. Let's take a look at the previous lab, right? In the previous lab, which was number 5. There you go. That was lab number 5. That's the simplest of all circuits they are going to see in your life. Okay? That was the previous lab. Previous lab. In the previous lab, we work with the simplest circuit that you will ever see in your life. A circuit with a battery and a single resistor. Okay. Think in today's lab, we will work with the next, with a circuit that is in the next level of difficulty. A circuit with a battery and 2 resistors. And 2 resistors in series. Okay? I think resistors in series, circuits resistors in series, is simpler. Next in difficulty will be a circuit with 2 resistors in parallel. We're going to see how it looks like. We'll do that today as well. Okay? 2 resistors in parallel, or elements. So, run the simulation. First circuit, battery switch resistor 1 and resistor 2. Resistors are in series. This is the second simplest circuit you ever see in your entire life. In this type of circuit, we have only one track for the current. The electrons flow along only one track. It's like having a closed circuit in which the cars are racing. Okay, and there is no exits. There is just this oval circuit in which the cars move in circles. The current tracks, we have only one track for the current. The current doesn't split into multiple tracks. For this reason, we say that the current is the same throughout it. Remember the definition of current? The definition of current means the amount of charge per unit of time that flows through a given section of the wire. Okay? Any questions so far? So I will get my illustration here. I'm going to do my own illustration in my own PowerPoint slides. Let's see here. Here you go. I cannot, it's difficult to emphasize how important those circuits are. Here are capacitors in parallel and series. So let me show you one circuit. Okay, here you go. Okay, what you see right in here is a circuit with a single resistor. Okay, I should have shown that before. So if you have a resistor here, the resistor has electrons. Okay, and have protons too inside in the at the microscopic level. And those electrons are what we call the valence electrons. Remember the valence electrons in chemistry that we studied? What's the interesting part about the valence electrons? The valence electrons, they can move more easily from atom to atom if you have a metal conductor. And those are the electric charges that produces the current. Okay, the electric charge that produce the current are the valence electrons in the metal that makes part of your circuit. That's the picture you must have. Another way that you can see it, think about the copper wire, right? Circuits are made of copper wire. We use copper wires because they're cheap. We could use gold wires, we could use silver wires, we could use tungsten wires, but they're either too expensive compared to copper, or they don't have as good as a conductivity. Okay? And that's how we have what I have here. I have the valence electrons inside the copper wire. If we also have protons. Okay? I'm not picturing the protons here. The net charge of this wire is 0. We have electrons and protons there. And right now, those electrons are just moving in a random fashion. Back and forth. They don't go anywhere. They're just oscillating in the horizontal, oscillating in the vertical, and so on. Okay? When we connect this copper wire to a battery, that's the symbol of a battery, and that's what we did before in the previous experiment. Okay? The electrons inside the copper wire, they start moving. Okay? There you go. They start moving. First, what happens when you connect the battery? I gotta put my battery there. Here you go. That's the conceptual idea that you have to have in mind. It may be somewhat difficult for you to visualize right now, but as you get more and more exposed to that, it becomes more and more clear. Okay? So the moment I connect my battery, something interesting happens in this copper wire. What happens? Okay, an electric field is established right in here. And this electric field is a uniform electric field. We discussed that before. What happens to a uniform electric field? In a uniform electric field, the electric charges start to move. There is a force applied to each of the charges. And because of this force, the electric charges start to move. Okay? It's like we have, when you put a battery here, it is as though that we have a distribution of positive charges on this extreme of the wire and a distribution of negative charges on the other extreme of the wire. That's a very good way to picture what happens inside the wire. And those lines here, broken lines, are the electric field. The electric field inside the wire. With the electric field that inside, the negative charges that are inside in the bulk of the wire are going to be exposed, are going to be subjected to a force, to an electric force, and the charges are going to move. The negative charges are going to move towards the positive side with a given velocity. This velocity has a name. This is the drift velocity. Okay? What is the electric current? Here you go. I should have shown that to you before. Okay? The electric current, suppose that we put an imaginary gate here in this wire. A very good way to visualize. Here you go. Here's the observer. Oh, here's the observer. Someone with a big eye there. The gatekeeper, right? The gatekeeper is going to monitor how many electrons go through this gate. So this is imaginary gate. The current, the electric current, is equal to the amount of charge that flows through this cross-section, through this gate. So this is imaginary gate divided by the amount of time. In other words, is the number of electric charges, electrons that cross this gate, times the electric charge divided by delta T. That's what an electric current is all about. It's a very simple concept. And the charges are moving in tandem to the right because we have that battery that you connect to this copper wire that has some resistance, by the way. Okay, that's the picture you must have. Okay, so here you go. The current, the motion of the electrons is in the clockwise direction, but the direction of the current flow is contrary to the direction of flow of the negative charges. Okay, the current flow indicates the direction that the charge would move if the charge were positive. That's why the velocity of the electrons here is in an opposite direction as the direction of the current. Okay, so here you go. I'm gonna put another current here on the bottom, right here. Here you go. But now this current should be pointing on the other direction. Oh, here you go. Yeah, like that. Is this current here is the same as this one? It's just like this. You have this circuit, right? This moving the counterclockwise. There, the direction of the current is counterclockwise, but the motion of the electrons is not in a clockwise direction. Why is that? Because the direction of the current depicts the direction of motion of the positive charges, and the electrons are negative charges, the opposite charge. Opposite charge moves in opposite direction. Okay? So direction of the current flow is contrary to the flow of electrons inside a wire. Okay, but here you go. Those electrons, here you go. Here's the force applied to the electrons. If there was no resistance in this wire, if there was no resistance whatsoever in this wire, those charges just would keep accelerating in the circuit, just like it happens in a superconducting circuit. Okay? But because most materials has an electrical resistance, which is the electrical counterpart of friction, this resistance is going to oppose this electric force. And the charges are going to move, but they are going to move with constant velocity. A constant drift, we call it constant drift velocity. That's how you should picture. Okay? Though this resistance is due to non-uniformities in the copper wire. Every material has some junk in there. Not just junk, but also positive charges that attract the electrons, don't let them move, you know, things like that. That's the picture that you have to have of the electrons inside. It is those non-uniformities, and the positive charges in the metal that affect the resistance of the material. Okay, we do know that the resistance depends on the length of the material. It's directly proportional to the length of the material. The longer the wire, the more resistance you have. This wire here has more resistance than this one because it has more non-uniformities along its length. We also know that a thicker wire has less resistance than a thinner wire. A thicker wire, it is as though you have a very wide freeway. That's what it is. That's the very good analogy. Here what you have a very wide freeway that lots of cars can move through, so they have less resistance. Here's a very narrow highway that less cars can move. So the resistance is directly proportional to the length, inversely proportional to the area, cross-sectional area. This is the cross-sectional area of the wire. What else? Here you go. Here's the circuit that we did last time with a single resistor. I'm not illustrating the switch that we had there before. The battery, right, and the current moving the circuit. Here is the resistor. That's the symbol for the resistor. And now that's the one you're going to do right now. we are going to do a circuit with 2 resistors. Circuit with 2 resistors has the same current throughout it. Remember that picture of the gate, the imaginary gate along the circuit? See, here is one of those gates there. The same amount of electrons that flows through here is equal, the number of electrons that flows through here is equal to the number of electrons that flows through this gate. And the number of the electrons that flows through this gate as well. Can you picture that? So elements in series, elements that are connected in series in a circuit have the same current flowing through them. That's the circuit, okay? Here you go. And what is going to change? What is it going to change? What's going to change is the electric potential, is the energy. When the electric charges enter the resistor, we have very little resistance here in this wire. But when the electric charge enters the resistor, it's going to lose a great deal of its potential energy, of its energy that was given, supplied by the battery. And so we are going to have a drop of energy here, a drop in potential. Okay? We call it drop V1 and drop V2. This drop in potential is given by Ohm's law. V1 is equal to R1I. And what you're going to see in the simulation is that the drop in potential here plus the drop in potential here is going to be equal to V. Okay? So let's go there to the simulation. That's the picture that you have to have. Now we're gonna go to our, here you go. Using a battery, a switch, and color-coded resistor, build a circuit in figure 10.7. Remember to select any of these elements. Select any of these elements, click on the element and drag the place. All right, we did that already. Set the source voltage, the potential difference to, first to 0, just like he did before. Oh, wait a minute. This is 5. Sorry. We want number 6. We want this one here. Here you go. Yeah, the resistor that they illustrated here doesn't have the color bands. That's why I put this note here. Set the source voltage to 5 volts. Let's do that. Set the source voltage to 5 volts. Click the battery, decrease the voltage to 5. Now I overshoot, right? So I have to increase to 5. Here you go. What's next? Remember to change, set the resistance of the resistor in the horizontal line to 47 ohms. Here you go. Gonna click it here and increase it to 47. Here you go. You got it. What about the other one? The other one you wanna put it 100 ohms. There is some limitation of how high the resistance you can go in this simulation, okay? Let's see, 100. Here you go. Are these resistors in series or parallel? They are in series. Is it the current or the voltage that's the same for these 2 resistors? Find the equivalent resistance. Okay. So let's see. Are these is it the current or the voltage that's the same for these 2 resistors? I told you, right? So you gotta have that picture that I told you of the gate, of the imaginary gate flowing through these wires. Is the current that's the same? What's not the same is the voltage. The energy ends up being split between those 2 resistors. The voltage, the energy per unit charge ends up being split between those 2 resistors when we apply a voltage. Here you go. What next? Oh, find the equivalent resistance. What I didn't tell you is the equivalent resistance of this circuit. resistors that are combined in series, we can prove that mathematically, by the way. When you combine resistors in series, they act as though as they are a single resistor with a resistance equal to the sum of the elements. Okay, like that. Equivalent, we call that the equivalent resistor in a resistance in a circuit. I have this illustration here in my PowerPoint. Here you go. We have the circuit with two resistors. This circuit with two resistors is equivalent to a circuit with a single resistor, a simpler circuit, but the resistance is going to be R1 plus R2. That's the equivalent resistor, the equivalent circuit with equivalent resistance, R1 plus R2. Okay? Current is flowing through the circuit. That's what that guy is asking, and that's going to be part of the lecture as well. Okay? Let's go back. You go. If you have n resistors in series, the equivalent resistance is going to be the sum. But that's for the resistors in series. N resistors in series. Here you go. If the resistors are in parallel, the situation is the inverse one. See, the inverse. I have exactly the inverse here. See that? Instead of the sum of the resistances, we have the sum of the inverse of the resistances. The equivalent resistance, formula is the inverse, sort of inverse. It's very easy to memorize, right? And has all to do with Ohm's law. Has all to do with Ohm's law. So here you go. Let's go. Okay, so find the equivalent resistance. Should be R1 plus R2, which is 100 plus 47, which is 147. And now we are going to find out the theoretical value for the source current. Okay, and I'm going to do that in my software, my favorite software. Investigations, lab, electricity, right in here. Recall Ohm's law. Ohm's law. Here, I'm going to write that down here. Ohm's law, right? Ohm's law is V equal to R times I. Can you remember that? Ri, resistance times current. The current decreases the resistance, right? I'm going to show you that to you. Here you go. The current, user defined, decreases with the resistance, inversely proportional to the resistance. So what is the voltage there in my battery? Let's see. Before we move forward, let's make sure that I gotta quit this one here. I don't need that. Let's get this one right in here. We gotta set the voltage to 5 volts. I didn't do that yet, right? Let's do that together. Set the voltage to 5 volts. Oh, I already have it. Good. Forgot it. So before you close the circuit, before you put the ammeter in there, let's calculate what's supposed to be the current. And the voltage across each resistor. Show your work. And we're going to do that here. Here you go. But here you go. The resistance actually is going to be the equivalent resistance. Okay? And I want to know the current. The voltage is going to be 5 volts. The equivalent resistance is going to be R1 plus R2. R1 plus R2. R1, we know that we put that as being 47 ohms. R2, 100 ohms. Okay? Gonna put those guys all there at the top because they are Ohm's law. Here we go. I'm gonna put circuit in resistors in series. Okay. Resistor in series. So I'm going to substitute right here. Ohms. V R1 R2. Here we go. See? I get 5 divided by 147. Let's see what we get. Expand. No, it doesn't do it. Calculate. It doesn't do it. Oh man, that's because of those guys here. Let's see if I can get. I don't want that. So what I'm gonna do, volts is equal to amps times omega. That's Ohm's law, Ri, right? The unit of volts is equal to the unit of amps multiplied by the unit of ohms of the resistance. Calculated, that's what we get. I get a current of 0.034 for this specific case, 0.034 amps. 123 is 34 milliamps. That's a reasonable value, 1, 2, 3, 4, a current in a circuit. So let's see if we got that. You go show your work, record your values along with the appropriate units in column 2. Oh yeah, here you go. So you gotta put this table together. Current source, then you gotta tell me the current through the first resistor, the current through the second resistor. You should know all those three values should be the same because the resistors are in series. What is not going to be the same is the voltage. We can calculate delta V1 and delta V2. Call it delta V2, delta V1 and delta V2, but we can call it V1 and V2 as well. How do we do that? Well, we use Ohm's law again. We found, going back here to my circuit, we found the current through this circuit here. Now that we found the current, we go back to this circuit here that we had before. Remember, that's the equivalent circuit of this one. We go back to this circuit here, and we use Ohm's law through resistor 1. Ohm's law through resistor 1 is V1 equal to R1I. Ohm's law through resistor 2 is V2 equal to R2I. Okay, so let's do that. V1, the book calls that delta V1. I prefer V1. V1 is I times R1. V2, which we do not know, is I times R2. Let's go calculate that. R1I. Oops. R1I. Here you go. Amps omega. Let's not forget that omega is volts divided by amp. Ooh, I hate that. I hate when he does that, but that's okay. I'm going to substitute that right here, and we get 1.59 volts. Remember that the V is 5 volts, right? V is 5 volts. So R2, the V2 should be 5 volts minus this value. Okay? So there is a larger drop in voltage through the resistor 2 because it has a higher resistance. Let's do the math. Okay? Ri is here, R2 is right in here. Oh gosh. We go. Calculate. See? There's a larger drop in voltage across resistor number 2 because it has a higher resistance. That's the reason. You lose more energy at resistor number 2 than at resistor number 1. So you go ahead and log those values in your table. And then we are going to measure that theoretical value. Here you go, theoretical values. And then you're going to measure that with the simulation. Okay, it's 1:36 right now. Let me take attendance and we have a little break and come back for the actual simulation. Today is the 28th. Bella, are you there, Bella?
Here.
Good, thank you. Annabella?
Here.
Okay, let me make sure that we all get the simulation, right? Bella, are you running the simulation there, Bella?
Yes.
Okay, good. Annabella, are you running the simulation?
Yes.
I can hear you.
Yes.
Yes? Okay. What about Sarah? Are you running the simulation there, Sarah?
Yeah.
Yes? Okay. Let's see. Yeah, for some reason your voice came distorted. I do not know why, Sarah. Might be a problem with your microphone. So, Carly, do you have the simulation there, Carly?
Yes. Yes, I do.
Okay. Mahedi?
Yeah, I got it.
Okay. Wesley? Okay. Ada?
Yes.
Okay. I'm still tempting to call you Ida. You know, I grew up in Brazil, you know, this name is, we say Ida, but here in the States it should be Ada. Here you go. Jordan.
Yes.
Okay, thank you, Jordan. Donica.
Yes.
Shagar.
Yes.
Daniela Rodas.
Yes.
Good, thank you. Dior Simons.
Yes.
Okay, Shreya.
Yes.
Peter Girgs. Did Peter come in? I see Peter again, but he's not answering. No answer. Okay, I'll put a O here. Ana Ponce.
Yes.
Okay. Kaylee.
Yes.
Alisa Quintero.
Yes.
Jasmine Tobar.
Yes, I did it.
Okay, good.
Hey, Professor. Sorry, I missed them. Peter, I forgot to
Who is
say.
that?
I was muted. Sorry about that. I got it good though.
Okay, you got it? Okay.
Yeah.
Okay, so we have, we have 18 students right now. It's 1:39. Let's have a break until 1:55. Lecture, lab notes. Here you go. Break till 1:55 p.m.